hello everyone. Disregard everything that's on the screen. We're not going to worry about it. We're going to go to this one. Today I will be giving a brief overview of Pytorch and how it works. Pytorch is a machine learning Python library that people use. So it's honestly more, so there's two main ones. There's Pytorch and then there's TensorFlow. And TensorFlow is honestly, in my opinion, big and scary and not human readable. So that tends to be more what people use like companies in production. And then PyTorch is more like academic and research friendly because, you know, it's like in words and you can read through it and everything seems to make sense. Just a tad bit more. So I decided to start with this one. Okay, if you're installing PyTorch, you can do pip install PyTorch or conda install PyTorch. However you do your Python libraries. There's some other things you might want to install, like Torch Vision is really helpful as well. Or you can go in here to the link and they have a thing that you can click, like, do you have a Linux, do you have a Windows? And then they'll give you a new thing to put down here. And you can just copy paste that into your command line and it'll install it for you. I can't get off this webpage. Cool. Also, let me maybe share this with you guys in the chat so that you can follow along with me. Let's see. All right, copy link, done. Can I find the chat? Cool. Okay. So I think this will make your own local copy of this for you. I don't think they have Google Colab that's like actually collaborative yet. But anyway, just in case you didn't know, I'm doing this in Google Colab, which is just basically Google has hosted like a Jupyter notebook on their own servers, so you can use their resources and their GPUs to train things, as opposed to your own computer, which may or may not have a lot of computing power. I just put the cats and the dogs on the top of my thing because they make me happy. And when you're dealing with a bug, it's just, you know, more fun to look at some animals. But anyway, the first thing that you can do is kind of import all of these packages. So Torch is just the base packet of PyTorch. Utils.data is going to have us import the dataset class and then the data loader. So with PyTorch, there's kind of 4 different things. The dataset class that you will make for whatever data you're trying to learn on. Today, we're going to do something with MNIST. The data loader, which is how you're going to get samples from your data set and pass it into your network. The network class, which is down here, which we'll get into very quickly. And then kind of the main loop in your code that's actually going to get things from the dataset class and then put it through your network and then compute the loss and back propagate it. And if you don't know what those things mean, we'll go over them. Or if I don't do it in enough detail, feel free to stop me. Okay, the first thing we can start with is your dataset class. So you're going to start it just kind of like this class sample dataset. You can call it whatever you want, as long as you put dataset in here. And this dataset is going to be the same dataset that we just imported. And for the init function, you kind of just want to put whatever commands you need in order to get your data. And so for us, we're going to be using the Torch Vision datasets class or package in order to get the MNIST data. So there's kind of 2 ways. PyTorch and Torch Vision, which are kind of like really connected, have a lot of the really common data sets available. So let's see if I have that open. Right. So they have a lot of the really common data sets. So MNIST is, do they have a link? Do they have a link that's interesting? No. Okay. So if you look at MNIST, it is basically just a whole bunch of digits. So it's just a whole bunch of pictures of handwritten digits with their corresponding labels of what number it is. So 0 through 9. And they have a whole bunch of other data sets in Torch Vision as well that it had a list for before and now it doesn't, but that's fine. Cool. We're going to be using MNIST. That's the only thing you really need to know. And so after that, the other two functions you need to have inside of your dataset class are len. And all of these functions need to have the underscores because you're overriding some functions from the underlying dataset class. And if you don't understand what that means, basically just you need to define what these functions do, and they look like this. So length, which tells the code kind of how many pieces of data that you have. So I just initialized our data here. And so just len of self.data will look into the MNIST object and see how many items it has and return that. And then get item. So get item is basically just saying, okay, what code would I have to run through in order to get one sample from the total data set that we have now loaded. And dataset classes can get more intense. So like if I'm going to show you an example of a dataset class, we can go here in the middle where I've written some stuff. And so like you can load routes, you can have things like paths, modes, things like that. And then you can also have like really extensive get items depending on like what kind of data you're loading in. So this is a dataset class that I wrote for some pedestrian trajectory data. So it basically just gives like over a certain number of time steps, it gives the XY positions of all the people in a certain scene, and then the images corresponding to just some overhead camera. And so there's just like a whole bunch of pre-processing that I had to do. So you can also have more functions in your dataset class that like do some pre-processing for you. It's not really important like what that pre-processing is, but just that it exists. So ours is really bare bones, but you can get more complicated if you so choose. So the next thing that we have is our network class. And for that, you really need two functions. First is the init function. And the first line in your network class is going to be super with the name of your network class and then self. And what this does is your network class is going to be how you're defining the architecture of your neural network that you're going to use to learn whatever you're going to learn about your data. And so we extend nn.module. And so this super line just calls whatever the init function is in nn.module, which kind of initializes all of the stuff behind the scenes that Pytorch uses to like back propagate the loss and do all of the stuff that makes it actually machine learning. But something you can do in here is like define layers. So we'll just make something really simple, like self-fc1 equals nn.linear. So what is this? nn is torch.nn, and that's kind of where they put all of the pieces that you can use to then make your neural network. So if we go to the documentation for this, they've got a lot of things: convolution layers, pooling layers, padding layers. If you don't know what that means, I think I might do another one of these later to kind of go over more in depth what all these different types of things are and what they're used for. But we're really focused on linear layers for now because that's kind of the most simple. So all this basically is it's getting some input and it's doing just xat plus b with just the line equation. And if you put a whole bunch of these in a row with non-linearities in between, and what I mean by that is activation functions, which they've got a whole bunch of different types. So, I mean, let's see some. We can do ReLU activation. So what that looks like is images. Basically just everything that's below 0 is 0, and everything above 0 is itself. Or they have sigmoid, like over here on the left, where it's not exactly clipping off everything at 0, but after a certain point, everything is 0, and then it kind of just goes up to 1. And they have another that's like that's really popular called tanh, where instead of stopping at 0 down here at the bottom, it's kind of like sigmoid, except it goes from 1 to -1. But we'll probably be using ReLU for the time being in this tutorial. So when you're defining the linear layer, what each of these things, the parameters that you have to pass are the input features first and the output features. And out features. And you may not exactly know what these are when you're first starting if you haven't done a lot of work with your specific data set. So kind of what I do when I start is, at least the in features, I leave completely blank because it's easier to just kind of have the code tell you at the end when you get an error message in your train loop, hey, you said in features was 10, but it's actually 16. And then you know to put 16 in there, as opposed to like, there's math you could do to figure it out, but it's very context dependent. So for this, let's just say we want our out features to be something like 128. So there's another convention that nobody really tells you about, but that kind of pervades, which is that the feature numbers that we use are usually always powers of 2, unless, except for the input features and the output features, that can be anything you want, like the internal ones. So we're going to define several layers of our model. FC2, just another linear layer. And this one will take in 128 and go 256. And I'm doing like sequential powers of 2, let's say, but you don't have to. So this can be, 4096. That's maybe too big. 1024. I think that's what it is. You'll have to fact check me on that after, right? But actually, they would have to still go in order because they need to go into each other, right? Okay, so just for the sake of the experiment, I'll make a couple more. 24, 2. And in the same way, like if you're going input features to output features, it doesn't have to be sequential powers of 2. And when you're going output features to input features, it also doesn't have to. So I could go right down to like 128 and then C5, I can go from 128 to, let's say, like 1. Because the data that we're using is MNIST, so it's going to be taking in an image. And typically when you're using images and you input it into linear layers, at least, what you do is you flatten out the image. So you take each row of pixels and you kind of just put them all together in a line. So you get one vector instead of like a matrix of values. And the labels that we have for MNIST are like the digits 0 through 9. So in theory, what we're going to have this network do is take in the flattened image and then output just whether it's a 0, 1, 2, 3, 4, etc., up to 9. And then we are also going to define our activation function, and that's going to be ReLU. So that doesn't, the activation functions usually don't take any parameters. There's special cases in which they might, but usually they don't. And the activation functions are important, if I didn't mention this before, because there's someone found out sometime in the past that if you just do all of these linear layers in a row, that you can kind of just equate it to one equation. So it's not actually like 5 different layers that we've defined. You could simplify all of the math to just be kind of one equation. And so that really limits the computational power of the network, let's say, which is why, it's called deep learning and not shallow learning. So what you really want is a whole bunch of different layers. And so the only way to make the math not reduce down is to have these nonlinearities in between each layer. So that's the init function, and at least the linear layers and the ReLU activation function. So for the forward, we're basically telling the network, hi, I'm giving you this input and I want you to do these operations in this order. So for the forward, let's see, we are going to pass it, I guess, just in the order that I've listed the linear layers. And after each layer, you want to do an activation function. So I'll kind of just do self.relu and inside self.fc1 and put in x, right? And then I can kind of do the same thing again, except instead of fc1, I can change it to fc2. And we do this for all of our layers. Now, depending on what type of layers you have, you may not actually want to just feed it in directly. You can do math in here. You can do other pre-processing steps. You can kind of like save this value as y and then feed it in, right? And then if you want to, you can like return that intermediate value. There's a whole bunch of different things you can do with this, but the most simple is just kind of feeding it through each layer sequentially until you get the final output, and then just returning that final output. If there's a shorthand for doing this, so if you know that for your network, you have kind of like the same type of input, and you want to do like the same 4 layers in the same order, instead of writing it all out like this, you could do something where, and I'll delete this later, but you can do something where you do nn.sequential. And then inside, you're just going to give it a list, right? So let's say, let me actually put this in here, right? So you could do, self.fc1 and then self.relu and then self.fc2 and then self.relu, et cetera, until you do as many of the layers that you know that you want. And then in your forward, you could just call something like return, I don't know, let's say that we called this hi, right? You could just return hi of x, right? And it would just put it through all of this for you. So the benefits of using nn.sequential is that if it's something that's literally just, I have these 5 layers, I want to do them in the same exact order with no pre-processing, you can kind of just type this once. And let's say I wanted to do this like 8 times before I returned the output, then I could just do, hi x 8 times instead of having to type out 16 different lines. But the benefits of doing it this way is that you kind of get more of a sense of what's going on with the data, and you have more ability to be able to, I guess, manipulate what's going on with the actual machine learning itself. Okay, so this is Google Colab. So I have to actually run these if I want this code to be available, right? Cool. Okay. So I guess let me pause really quickly and see if anyone has any questions about the dataset class and the network class before I go on. Okay. There's nothing in the chat. No one's unmuting. I'm going to take this as a no. Cool. Okay. So next, we kind of have the main event, which is the function that trains everything, right? So ignore this for now. I forgot how to get the cells to disappear in Colab. So pretend everything below this one isn't here. But let's say we have some function train, and in it we get some network that's already been defined. I'll go through how to define it later. We get some data loader, which will feed us each sequential piece of data from our data set. And I'll go through how to define that later as well. We have a device. And so with device, it's that you don't have to do machine learning on GPUs. The reason we do it is because it's exponentially faster. But you could do it on your regular CPU if you really wanted. And so the way that Pytorch determines whether you're using just your CPU or a GPU is by explicitly defining a device. And so I'll tell you how to define the device later. Basically, it just tells it, hey, am I doing this on the computer, the CPU, or am I doing it on this GPU? Epochs, so that's kind of how many times do you want to go over the entire set, the data set that we have. And then LR, which is learning rate. So that's kind of telling it how fast do we want our network to be able to learn. Typically for the learning rate, you would want to set it at definitely less than 1, usually like 1e negative 3, 1e negative 4, 1e negative 2, 1e negative 5. It's kind of something that people play around with. So that's what people mean when they say hyperparameter tuning. It's that kind of in the vein of training all of your networks, you might have even more parameters than just the learning rate. And so you kind of tweak them around to different values and different combinations of values if you have multiple variables that you're tweaking to see which one gives you the lowest loss. Okay, so the first thing we're going to do in the training loop, I guess, is define our helper functions that are really going to do the heavy lifting of the math for us. So the first is the optimizer. And that is the thing that's kind of figuring out what loss goes where in your network. So it kind of handles, it's a helper in handling the network backpropagation of the loss. And the backpropagation of the loss is what actually changes the network weights. So if I still have this open to the linear layer, what I mean by network weights is like this A network or this A matrix and this B vector are learned while you're going through iterations of the train function. And so when you're backpropagating the loss, that's how you're figuring out what weights in this A matrix and this B vector to change in order to hopefully get your input to be the correct output that you're looking for. So the first thing is the optimizer. The first thing you pass it is your network parameters by doing net.parameters. Then the next thing you pass it is the learning rate. And for this, we'll just do 1e negative 3. And again, you will really want to play around with your learning rate. One way that you can do that is by making a scheduler, which I have here. So I'm not going to go too much into it, but basically you pass it the optimizer, you tell it how many epochs you want to do. So how many times you want to iterate over the data. Let's just say we want to do it 10 times for the sake of this experiment. This is the data size. So I don't actually know how long our data set is. So one thing you can do is len of loader, and that'll tell you how long your data set is. And then this is kind of the lowest learning rate that you want to do. So what is the scheduler doing? Let's just look at an image of cosine really fast. Maybe I wanted to put in cosine wave. No, this is fine. Great. Okay, cool. So can I click on this image and have it be fine? A little bit. All right. So what the scheduler is doing is it's starting the learning rate up here at whatever you set it to be. So 1e negative 2, 1e negative 3, right? And then it's just slowly decreasing it until over the different epochs until you get down to the lowest value, which is whatever you tell it the minimum learning rate is. And the reason that this is important is because if you have the same learning rate, let's see if I can do, is there, oh, that's not stochastic gradient descent. Okay, be careful what you Google, children. There's no really fun images. Oh yes, this one, perfect. So when you're doing machine learning, the whole reason why it works is because it's a convex optimization problem. And what that means is of all the solutions, so like of all the output you could possibly get when you put in your input, it kind of fits inside of this oval here. And the output that we want, we position at the bottom here. And so whenever we are doing an iteration in the train loop, the learning rate tells us how big we want this step to be as we go closer and closer and closer to our goal. If we make it really, really big, like 1200, right? We'll just keep going from this side to this side, to this side, to this side, to this side, and we won't actually ever reach the bottom because our step size will be too big. So, but we can also see how it might be good to learn or have a higher learning rate at the beginning because we'll learn a whole lot really quickly, and then have a lower learning rate at the end as we kind of refine our search and get closer and closer to the ultimate value that we want. Okay, so that's why you would even want to have a scheduler to change your learning rate. The next thing that you're going to want to do is define a loss function. So for that, we go back to NN. The most common is MSE loss, which is mean squared error. So we're going to go back to our trusty Google word. Okay, so MSE is kind of, I don't know, I feel like a lot of people would have had exposure with it over the past. In the past, it's really common. But it's basically where you take the ground truth output, yi, you take whatever output you predicted and you subtract them, and then you square it so that all the values are positive. And then you basically just take the average over all of the different, I guess, items that you have that you've put into your network. And so that's how it's doing the loss for this. I wonder if this has a list of loss functions for me. It does. Cool. So anyway, there's L1 loss, which is really similar in that, oh, it doesn't have the equation. Okay. There's L1 loss, which is really similar, except that it just doesn't do the squaring, I think is the only difference. And is there any other popular ones? Okay, there's cross entropy loss, which is usually used for classification, which I guess, so in the example that I've kind of set up, we are doing a regression problem and not a classification problem. A regression problem is where you take in some input and then you ask the network to spit out like a number as an answer. So it's kind of the closest that you're going to get to what we would naturally think of as a math problem. A classification problem is where you take some input and then you ask it to produce a probability distribution over a set number of classes. So in our instance, instead of having a 1 here, we would put a 9. And then instead of using ReLU, or we could use ReLU, but we'd also add the sigmoid activation function. And so what putting a 9 here would do is that instead of the output being 1 number, it would be 9 numbers. And then what the sigmoid would do is that it would force the numbers that are actually in that output to be between 0 and 1. And so we could directly interpret them as a probability. And so what you would do is the class that the network was predicting would be the class with the highest probability in the output. And so you would use the cross entropy loss for that. But honestly, the longer I talk, the more I'm like, oh, I should give a whole one of these about that. But we're not going to do that today. We're going to use MSE loss, which you would just define exactly like this. Okay, I think these are all the helper functions that we needed. So just as a recap, we're doing the train function. We have our optimizer, which helps in knowing where to backpropagate the loss. We have our scheduler, which helps change our learning rate as we get further along into training. And then we have our loss function, which actually computes how wrong was our prediction from what we wanted it to be. And so what you're going to do next is do, for E and range epochs, which just will iterate over the data set epochs number of times. Then for data in loader, and what this will do is it will just get each sequential item from your data loader. And then depending on your dataset class and exactly what the data looks like, you could do some more pre-processing steps here, or it could be just so simple as to say output equals net data, right? Usually it actually won't be as simple because in this data will be both the input and the answer. So I guess you could have for data comma label in loader. And what that'll do is it'll take the tuple and it of input comma answer, and it will split it up into two different variables for you. So if you have done your dataset class right, and not necessarily right, but just as simply as possible, then this is all you need to do in order to get your network's prediction. In order to get the loss, you would just do loss func of your output and your label, and that's it. So then the next things that you want to do is opt.0grad. And the purpose of this is the optimizer deals with the gradients. And the gradients are kind of like, I guess, do I have that back open? So the gradient is kind of literally just the slope of this. So it's kind of how wrong you are. So our correct answer is down here at the bottom, right? Our prediction is this black ball. And so the gradient is kind of the line made between our prediction and our correct answer. And that kind of tells us how wrong we are. And so what we want to do is zero that out before we try to backpropagate the loss through the network, or else you kind of just get an accruing of losses over multiple different steps, and you don't really learn anything because you want to reset the learning pattern, I guess, every time you get a new piece of data from your data loader. So that's what opt.0grad does. The next thing you want to do then is loss.backward. And what this does is it actually tells Pytorch in the background with its magic to compute, hey, okay, cool. I know what I predicted. I know what the right answer was supposed to be. I know exactly how wrong it is. I want to use the information from the optimizer and what our learning rate is to then change the weights of the network. So that's all encapsulated in basically that one line, which is really good for us so that we don't have to code that anymore. Because back in the day, they were doing it by hand, and that seems less than optimal. Okay, if we were actually using the scheduler after this, we would do opt.step, which kind of just signals to the optimizer that you're done with your current iteration of learning, and scheduler.step, if I can spell, which tells the scheduler, hey, we were using this learning rate, but we're now on to like the next piece of data. So you should use the learning rate that corresponds to that one, since we are gradually decreasing the learning rate as we learn. And that's kind of your entire train loop, like bare bones right there. Some other things you might want to do is keep track of the loss, so total loss, right? Or even the loss per epoch. Epoch loss. And the way you would do that is we've computed the loss, we've done all of this, so we can just do epoch loss dot append loss dot item. And what this does is instead of whatever the complex graph is that allows the Pytorch backend to know exactly what weights to update in what way, it just gives us like the one number that signifies how wrong our predictions were from whatever label we actually wanted them to be. And so what people will do is this, and then something you can do at the end of every epoch is print, also, don't make fun of how I print things in Python. I don't want to append or concatenate strings because I'm lazy. And then torch.mean. Right, okay. So what this will do is it'll print out epoch, whatever number epoch we're on, and then tell you what the average loss is in that epoch. But then one thing that I like doing is seeing the progress over all of the epochs in terms of the loss for our learning. So you can kind of try to quantify is my model underfitting? Is it overfitting? Or is it learning what it's supposed to be doing? And I'll explain what underfitting and overfitting means in a moment. But for that, we would just do, total loss dot pend epoch loss, right? And then at the end, you could like, outside of the epochs, you could maybe like plot the total loss or whatever. Which, just in case you don't know Python, this is not a function. Plot is not a function. So that line will give an error and it won't actually work. But this is just kind of to remind you, you could plot the loss if you wanted to. Okay, so what do I mean by underfitting and overfitting? Let's go back to our handy dandy Google. I wish I could spell today, you guys. That would really be helpful. Okay, cool. This image here is perfect. Can we zoom? Great. So a really simplified way of thinking about machine learning is basically that you're just trying to find, especially because we're using linear layers, right? You're just basically trying to find the best line where when you put in your input, you get as close to the output you expect as possible. And so overfitting is when you find a line that's too perfect. And so it hits every single point to almost 100% accuracy, right? But that's of the data that it's seen. And so one thing that's really important about machine learning is it's your network's ability to generalize to new data, or else there would be no point to actually do machine learning, because if the only data that you have is data that you have answers for, then you could basically just use a lookup table, right? So with overfitting, if we have new data, let's say like this point, it won't really know what to do with it. It'll probably just drag it down to this line and put it down here when that's not actually where it would be. Where you have the exact opposite problem with underfitting, where like this probably isn't the best line to actually fit this data. It's not doing terribly poorly, so we have learned something, but you haven't like maxed out the capabilities of your network to be able to learn what you're asking it to learn. And so the middle is kind of what would look more balanced, a line that's like kind of in the middle of all the data. It follows a general trend, but like it's not literally going through every single point and contorting itself to be absolutely perfect. So that if I put a point, like somewhere over here, it's probably going to put it more close to where it's supposed to be, as opposed to if I did that same point over here, when it would pull it down to there with the overfitting. Okay. So, oh yes, okay. So now that you've trained your model and your loss has gone down really well and everything looks good. Oh, actually, let me see if I can. Do they give it to you in terms of what the loss curve looks like? Ah, yes, perfect. Okay. Word. So one way to figure out whether your model is overfitting or underfitting is by looking at the loss curve. And the loss curve you're going to want to look at is when you plot this total loss, right? Or when you plot the average loss per epoch. So if you do that each epoch, it should go down. So the orange line is whatever your test loss is. So this tells you how well your model is generalizing to unseen data. And the blue line is your training loss. So this is telling you how well your model can predict data that it's kind of already seen. And so you kind of want both to be as low as possible, but realistically, your training loss is always going to be lower than your test loss because your network has literally seen the answers before. With this, it's underfit if both lines are kind of going down pretty much equally. It's the best fit when both your test loss and your train loss have kind of gone down as long as they could have and have plateaued. And then you know that you've overfit when your training loss starts to go down, but your test loss then starts to go back up. And that tells you that your model has lost the ability to actually generalize to new information. Okay. Ooh, don't zoom out that far. Okay. So now that you have successfully trained your model, if you end your Python program here, you lose all of your your progress. So we want to save the model. What we do is the thing that you wanted to save is your network state dict or your state dictionary. And then you can just give it some cool name. Save cool model here, .pt. And so this is kind of just telling it the state of all of these different things that we put in it. So it saves the weight of this and the name of that layer, the name of this layer and the weights of this layer, et cetera, all the way on down. Because in theory, you could save a lot of different models with a lot of different numbers of layers, a lot of different types of layers. And so the state dict kind of tells Pytorch the structure of your network and then what the weights are that you've learned. That way it knows, it won't try to load the weights of a network that don't match the parameters that you've set here. That way you know you're loading the right network every time. And then this is just some random name that I've made. You don't have to end it in .pt if you don't want to, but that's it's another one of those unspoken conventions where PTs for Pytorch. So they just save their models with a .pt at the end. Okay. Oh, there is something I forgot. Okay, so in here, what you will want to do, either outside of your train function or in your train function, I'll do it in the train function since we're here now, is remember when I was talking about the device, it tells Pytorch whether to keep all of your data on your GPU or your CPU. You're going to want to explicitly tell it to put your things there. So net equals net.toDevice. That's how you kind of cast your network and your data to either your CPU or your GPU. So you have to do it with your network, and then you would also have to do it with your data as well. And in your loss function, you'll also, if you do it with both your network and your data, you'll also have to do it with the label. Now you have the, I guess, capability to ignore device altogether, in which case Pytorch will just default to CPU, and so you'll never have to do this. But if you're training with like images or lots and lots and lots of data where it takes a long time, you'll want to switch it over to the CPU. So you'll want to do this. I'm checking. Okay. I think this is actually everything that you need to do in your train. So now the fun thing is, for the test loop, you can kind of just copy paste, right? So in the test loop, you usually don't iterate over your data more than once. And so all you really need is this data part here. So everything underneath the loader. So one thing that I like to do at the beginning of my test loop is load my model. There's a thing where you could probably return your model from train and then actually use that to pass it to test. But there might be some conditions, especially when you're trying to figure out where you're overfitting or underfitting, where you only save the weights if it's like the best model and it has the best loss. So I guess just to kind of be safe, I load it from the memory every time. So the way that you would do that is by doing, okay, so you would still need to pass it net. And this net that you pass it would just be like a standard network, which I'll tell you how to define in a minute. But you do net.load state dict, and then torch.load, what did I call it? Save cool model here, .pt, or insert model name, whatever you call it. So now you have put the weights that we learned in our train loop into kind of our empty model that we had before. So now the model in this loop versus this loop is exactly the same. One thing I did forget also is that here you want to do net.train, and this kind of just tells Pytorch, hey, we are in the mode of training our network right now. as opposed to in the test, you'll want to do net.eval, where you tell Pytorch, hey, I kind of want to freeze all the weights where they are. I don't want to do any learning, and we're only using our network to get answers from. We're not trying to do any learning. That's what eval does. And then another secret that kind of helps with not changing the weights once you've learned them is doing with torch.nograd. You can either do it like this, or if you're just really into Python, you can do at torch.nograd, and that'll just apply the function to the entire test function. It's up to you. I didn't really know about this top thing for the longest time, so I tend to not do that and just put it in here. So what torch.nograd does is it kind of turns off the part of Pytorch where you are computing the loss, or like computing the big graph that tells it, okay, this is the loss, these are the weights I need to update. And that'll actually make it run a lot faster, because the thing that takes the longest with training is usually this lost at backward step. I mean, unless you just have some insanely long network, which even then, it's still the lost at backward that's going to take up the most time. So this kind of just gets rid of that, make sure we're not changing any of the weights, cuts down on some training time and some memory usage as well. So in there, what you'll want to do is go over the loader. Oh, you'll also want to cast your net to the device. And so in this loader, you'll have net.toDevice. You can still compute the loss, right? But you don't want to do any zero grad of the optimizer. You don't want to do any loss up backward, and you don't want to step anything. And so you all also probably want to keep track of the loss. So just test loss. So you can, oh, I didn't define the loss function, did I? Okay, let's do that also. Loss func equals nn.msc loss. Cool. So this is kind of the entire test loop here. You load the network, you set it to eval mode, you put it on your device, and then you initialize your loss function, and you keep your array that you're going to use to keep track of your loss. You make sure that you're not computing any gradients. You step through the data loader that you have for your test data. You get the output from the device. You figure out how far away it is from the actual output you wanted, and then you append it to keep track of it. At the end of it, you can, plot loss, which again, not a real command, but you can plot the loss. Another thing you can do is keep track of the predictions. So something I like to do is pred equals this, real equals this, right? And then each time we're here, I'll do dot append output, and then real dot append data. And that just makes it really easy so that you can do something like, plot preds versus real. And that way, instead of just trusting the loss number, you can actually see qualitatively, I never know which of those words it is, but you can actually see how close your predictions are to your actual labels. And then, so the other thing to mention is that the way that Pytorch deals with data is by converting everything to a tensor. And it's basically just a fancy NumPy array, but it does take up a little bit more space in memory. So I kind of just do .numpy on each of these to get rid of kind of any of that. And I have 5 minutes, so let's be really fast. Okay, how do you define the device? What you will do is device equals torch.device. And then this is just kind of standard. So CPU, CUDA, which is the shortcut for GPU. I don't really have time to get into it, but just CUDA tells it to do the GPU. If torch.CUDA.is available, probably has an underscore in it, else CPU. So that's kind of standard. What it does is it says, have the device be the GPU if the GPU is available, because usually if you have one, why not use it? And otherwise have it be the CPU. The way to define the network, right, is so net equals, what did we call it? Sample net. Okay, let's actually have the init function taken in features. That way you can maybe adapt it to different types of input. And so what you would just do is net equals sample net, and then give it in features. Let's say it's 12. It probably won't be 12, especially if it's images. It'll probably be something like 2000, 2048. I don't know. It really depends on what data you're using. And then you'll have to define something like epochs equals 100, or learning rate 20 - 3. I think I hard coded it in the test. I did, but you can have it equal to the learning rate from here. And then you can just kind of call the train function. So train on the network. Ooh, the data loader. Okay, so for that, we need to call the data class. So in order to make the dataset class, you just do this. What do we call it? Sample dataset. And I don't think that we gave it any, yeah, so we didn't give it any parameters for the init function, but if you wanted to like give it the path, you could put it in there. So instead of me just setting the root here, or if you want to read data from a specific folder on your computer, you could kind of have it do that. Okay, so then for the loader, you just kind of do data loader with your data set first. There's some important things like set pin memory. Pin, I think it's just pin memory. Yes, so you'll want to set that equal to true if you're using your GPU, and that just helps you load the data faster. Another useful thing is shuffle. So instead of reading your data like one after the other in the order that it is in the file, it can kind of jump around a little bit, which will help your model with generalizability. And there's a couple other things that you could set as well. So we will pass that into loader. Device. We specified our device, epochs, and learning rate. And then you would just call test after it with net device and loader. And so the only thing I've missed in my 2 minutes left is that when you're making your dataset network, this is actually perfect. So you want to give it something like mode equals train. And you don't want to use the same data to both train and test your model, because then how will you know if it can generalize to things it hasn't seen if it's seen all of the data? So one thing you can do is like if mode equals train, you can just kind of constrain it so that self.data equals just like 80% of data. Can I do math and talk at the same time? Is a great question. Okay. Hey, don't do that. I didn't ask for that. Okay. So else, so if mode isn't specified as train, then in theory it will be test. Then you set it to be the other 80% of the data. And that way, if it's train, it'll be using one set. And then if it's test, it'll be seeing unseen data, and you'll be able to tell if it can generalize or not. And the way that you would specify it in here is that when you're doing the data set, you need to do, mode equals train. Oop, train is a string, isn't it? And before you do test, you would just do mode equals test and then reload the loader as well. And so that's kind of the backbones of Pytorch. I am right at time, but I will take any questions if anyone has it. And I guess I'll have to do another one of these to go into things a little bit more in detail, so we can actually see it run at some future time. So yeah, any questions, any comments, any concerns?
Yeah, so could you start over again at slide one? I kind of lost you there. I'm just kidding. No,
um,
it
I
was
was like,
actually
well, I
a
don't
really
have
good presentation.
slides, but if you want to see it again, we recorded
Yeah, yeah, that's
it.
fair. No, I thought it was actually a really good presentation. Good job, Dave. I thought it was really clear. Well done.
Thanks. I guess stay tuned for part two. Uh, like you all, I am a student, so I don't know if that'll be this semester, but definitely next semester at the latest.
Cool.
I have one quick question.
Mhm.
When you have the network and everything saved, what's the easiest, or I guess the most common way of actually connecting it to a robot if you want to run it? Do you have a file that you save the network as, or do you have to have some kind of a board installed?
That's a great question. So I don't have a ton of experience with that, but I guess so. In that case, I guess I wouldn't use Pytorch. I think they have like Pytorch Lite or something, which just basically does all the things of Pytorch, but with less memory, because I'm assuming if you're uploading it to a robot, you have like processing constraints or memory constraints. Um, and I guess it would be kind of the same in terms of like defining the model code and running the model. I think there is a way where instead of like having to define the model and then load the weights, that you can just kind of save the network as like one chunk, like one thing, and kind of just use it. But I'm not really familiar with how exactly you would do that.
Gotcha. I'm sure there are plenty of different ways. Like you said, it depends on the robot.